In section 2, we will consider a function called a quadratic form. A quadratic form on Rn space is a function, whose value at a vector x can be computed by this form, where x is an n by n symmetric matrix. And at this point, this matrix A is called the matrix of the quadratic form. In example 1, let us consider the quadratic forms corresponding to these two matrices. So A is a symmetric matrix, and actually this is a diagonal matrix. The off-diagonal entries are zeros. And in case of B, we have a still symmetric matrix, but we have this non-zero off-diagonal entries. So if we consider the matrix A in problem A, then since A is a diagonal matrix, when you multiply x transpose and x to A, we get 4x1 squared plus a 3x2 squared. In case of B, we have -2 entries in the matrix. So when we consider x transpose A times x, when you consider this multiplication, we have this final result, and at this point we have this cross product term, and this term is obtained since we have these two non-zero entries in the off-diagonal areas. So if we have non-zero entries in the off-diagonal areas, then we have this cross product term as in B, but as in A, if the matrix is diagonal, then there is no cross product term. Okay. Given some invertible matrix P, if X is a vector in Rn space, this equation, or simply this equation, is called a change of variable. Okay. Now, if P is an invertible matrix, then if V1 up to Vn denotes the columns of P, then this V1 up to Vn, these vectors will be a basis of Rn space. So x equals to Py just represents x as a linear combination of V1 up to Vn using components of y vector. So this y from this change of a variable equation just represents the coordinate vector of x relative to the basis of Rn determined by the columns of the P matrix. If I combine this change of variable equation with the quadratic form x transpose Ax can be written in terms of y vector by P times of y transpose times A times P times of y, and eventually we have y transpose times P transpose AP times y vector. In other words, this is a quadratic form with y vector, and at that point P transpose AP is the matrix of the quadratic form. Since A is a symmetric matrix, A is orthogonally diagonalizable, so that means we can choose P so that P transpose AP becomes a diagonal matrix. So since A is a symmetric, theorem 2 in the previous section guarantees that we can find some orthogonal matrix P such that P transpose AP becomes a diagonal matrix. Then the quadratic form in the previous slide can be written as Y transpose dy, and since D is a diagonal matrix, this quadratic form in Y variable does not have the cross product term. Let us consider example 4. So we have a quadratic form Q in terms of x1 and x2. Okay? We want to transform this quadratic form so that it does not have any cross product term. Okay? Then we have to find the matrix of the quadratic form A, and then we need to orthogonally diagonalize the matrix. So here Qx is x1 squared minus 8x1 x2 minus 5x2 squared, and we need to split this negative 8x1 x2 into two parts, x1 squared minus 4x1 x2 minus 4x1 x2 minus 5x2 squared. Okay, then the coefficient of x1 squared goes to the first row first column. This next negative 4 goes to the first row second column, and second row first column, and negative 5 goes to the second row second column. And then if I multiply x1 x2 and x1 x2, this row vector, you get this Q, right? So the matrix of this quadratic form will be 1 minus 4 minus 4 and negative 5. So we need to find eigenvalues and orthonormal eigenvectors. So we need to consider the characteristic equation. A minus lambda identity has zero determinant. In other words, 1 minus lambda minus 4 minus 4 minus 5 minus lambda has the determinant of 1 minus lambda minus 5 minus lambda minus 16. So we have lambda squared plus 4 lambda minus 21, which is lambda plus 7 times lambda minus 3, and there should be 0, so we have two eigenvalues, minus 7 and 3. When lambda is minus 7, A minus lambda identity will be 8 minus 4 minus 4, 2. So this times x1 x2 will be 0. So when x2 is 1, x1 will be 1/2. So any multiple of this will be an eigenvector. Since we need a vector of length 1, we can normalize this vector to get the square root of 5, 1 over square root of 5 and 2 over square root of 5. Okay, and when lambda is 3, we have A minus lambda identity becomes minus 2 minus 4 minus 4 minus 8. So this times x1 x2 will be 0. So when x2 is 1, x1 will be negative 2. So any scalar multiple of this vector, okay, will be an eigenvector. For instance, plus minus 1 over square root of 5 times negative 2 and 1 will be on orthonormal eigenvector. Eigenvector of length 1, and that will be orthogonal to the previously found this eigenvector. Okay? So we just found two eigenvalues and corresponding eigenvectors with length 1, and these vectors are orthogonal because they correspond to distinct eigenvalues. So these two eigenvectors are orthonormal basis for R2 space. So if we construct a P with those two orthonormal eigenvectors, and this first column is an eigenvector corresponding to the eigenvalue 3, and the second column is the eigenvector corresponding to negative 7. So we define this matrix D with the 3 and negative 7 in this order. Then this A is orthogonally diagonalizable with these two matrices. In other words, A can be written as P times D times P inverse. Or in other words, this D is just P inverse times A times P. And since P is orthogonal, P inverse can be replaced by its transpose. Now let us consider the change of variable equation. So if I define y vector through this change of variable equation and with this P matrix, okay, then the quadratic form can be simplified. So the quadratic form Q in terms of x variable can be written with respect to the matrix A, and if we consider the change of a variable using this P matrix, and here P is constructed using the orthonormal eigenvectors of A matrix, and in that case, when you perform this transpose, we get P transpose AP, and since A is orthogonally diagonalized to this D matrix, and please remember that this D consists of corresponding eigenvalues of matrix A, and the quadratic form is simplified to this. In other words, when you directly multiply y1, y2 with this eigenvalue matrix the D and y1, y2 column vector, we get this 3y1 squared minus 7y2 squared without cross product term. Let us consider this quadratic form for this x using this new quadratic form. Okay, y from the change of a variable is P inverse times x, and since P is an orthogonal matrix, you don't have to compute the inverse. You can just take the transpose to get the inverse of this orthogonal matrix P. Okay, so y is P transpose times x. So after the transpose of P matrix, if you multiply x, you can find the values of y vector. So the quadratic form, new quadratic form with respect to y1 and y2, okay, can be computed with this 6 over square root of 5 and negative 2 over square root of 5 to get 16, and this is qx value when x is 2 and negative 2. So the original quadratic form with respect to x will give you the value 16, or you can introduce new variable y, and then you may consider the quadratic form relative to y vector and this diagonal matrix D, and so you can consider this composite mapping to obtain 16 instead of the original mapping Q with respect to x vector. we can generalize this result to get this theorem 4. So if A is an n by n symmetric matrix, then this A is orthogonally diagonalizable. So there is an orthogonal change of a variable which transforms the quadratic form x transpose ax into a simpler quadratic form y transpose dy and here it is simpler in the sense that this quadratic form does not have any cross product term, which will help you find the maximum or minimum, okay, of this function. The columns of P in theorem 4 are orthonormal eigenvectors of the matrix A, right? And these orthonormal eigenvectors will construct a basis for Rn space. Okay? And these n vectors may be called the principal axis of the quadratic form. Then the changeable variable introduces y vector, and that was the coordinate vector of x relative to the basis, and at this point this basis is given by the columns of P matrix. So in other words, this y vector is the coordinate vector of x relative to orthonormal basis of Rn given by these principal axes. Now let us consider some geometric meaning of this quadratic form, okay, where A is an invertible 2 by 2 symmetric matrix. So if we consider x vectors in R2 space satisfying this equation for some constant c, then actually x1, x2 times a11, a12, a21, a22 times x1, x2 equals c will give you a11 x1 squared plus 2 times a12 x1 x2 because a12 and a21 are the same, and a22 x2 squared equals c. So if a11 and if a22 are non-zero and if they are the same, then the x1 x2 pair satisfying this equation will define a circle. If a11 and a22 are non-zero and if they have the same sign, then x1 x2 pair satisfying this relation will define an ellipse. And if a11 and a22 have opposite signs, then x1 x2 pair will define a hyperbola, and so on. Okay? If a12 and a21 are zeros, in other words, if A is a diagonal matrix, then the equation will be a11 x1 squared plus a22 x2 squared equals c. So it will be an ellipse or circle if a11 and a22 have the same sign, or hyperbola if a11 and a22 have opposite signs. In other words, it is very easy to understand the figure corresponding to this quadratic form if A is a diagonal matrix. Let us look at the ellipse on the left hand side. Okay, out of all the points on the ellipse, we can find the point which is farthest from the origin. Those are these 2 points. This is the farthest point from the origin, and also we can easily identify the points which are closed to the origin. If this equation of the ellipse corresponds to x transpose lambda 1 0 0 lambda 2 x equals to 1, then this 1 over a squared is lambda 1 and 1 over b squared is lambda 2. So this distance from the origin to the farthest point is a, and that is 1 over the square root of the lambda 1, and the distance between 0 and b will be 1 over square root of lambda 2. Of course, I'm assuming that lambda 1 is smaller than lambda 2. Okay, so we can easily measure the distance, okay, from one of points on this ellipse to the origin, okay, if A is a diagonal matrix, and we can derive similar results for this hyperbola, right? If A is not a diagonal matrix, then we have a cross product term. So that means our ellipse or hyperbola are rotated a little bit. So if we draw the plot or figure with respect to the direction of eigenvectors y1 or y2, then we can easily identify this farthest point or the closest point. But in terms of the original variable x1 and x2, it is very difficult. Okay? So, given a quadratic form, we want to find the principal axis determined by the eigenvectors. Okay? And that will help you find, for example, the minimum distance, maximum distance, or directions of the farthest point or the closest point, and so on. Given a quadratic form Q, we say this Q is positive definite if Qx is positive for any non-zero x vector. Please note that if x is 0, then quadratic form will have value 0. Okay? And we say the quadratic form Q is negative definite if Qx is negative for any non-zero x vector. And if Q assumes both positive and negative values, then we say this quadratic form Q is indefinite. Okay? And if we allow the equality in this inequality, then we put semi in front of definite. In other words, we say the Q is positive semi-definite if Q is non-negative for any x vector. Okay, and we don't have to exclude 0 in this case because 0 is included in this comparison. And we say Q is negative semi-definite if Qx is non-positive, okay, for any x. For instance, if I consider 1, 0, 0, 2 matrix, then the corresponding quadratic form is always positive for any non-zero x vector. So this quadratic form is positive definite. If I consider negative 1, 0, 0, negative 2 matrix, then corresponding quadratic form is always negative for any non-zero x vector. So this quadratic form will be negative definite. If I have 0, 1, 0, negative 2 x transpose x, then depending on the components of x vector, this quadratic form may have positive value or negative value. So this quadratic form will be indefinite. Theorem 5 generalizes the examples I explained on the previous slide. So suppose that we have some n by n symmetric matrix A. Then the quadratic form x transpose AX will be positive definite if all the eigenvalues are positive, and vice versa. If that quadratic form is positive definite, the eigenvalues will be positive. And if all the eigenvalues of A are negative, then the quadratic form x transpose AX will be negative definite. And also, if the quadratic form x transpose x is negative definite, then all the eigenvalues of A will be negative. If A has both positive and negative eigenvalues, then the quadratic form will be indefinite. Okay? Let us prove this theorem. Since A is an m by n real symmetric matrix, A has real eigenvalues, and we can find n orthonormal eigenvectors. With these n orthonormal eigenvectors, we can construct the matrix P. Okay? Then we can write A as the product of B and D and P inverse. Or since P is orthogonal, A can be written as P times D times P transpose. Or in other words, P inverse times A times P will be a diagonal matrix D. Okay? Now, if we think of the change of a variable from x to y, and then if I replace this x with P times of y, then this will be y transpose P transpose A P y, and the product in between P transpose AP is just the D matrix, and since D is the diagonal matrix of eigenvalues lambda 1 up to lambda n, this product just results in this summation. And of course, lambda 1, lambda 2 up to lambda n are the eigenvalues of the matrix A. And since P is invertible, there is a one-to-one correspondence between all the non-zero x vectors and all the non-zero y vectors. Especially if x is non-zero, then y, which is P inverse times x, cannot be zero, right? If y is zero, then P, the invertible matrix, maps the zero vector to zero vector, so x should be zero, right? So if x is not zero, then y from x vector cannot be zero. And if y is non-zero, the x vector, if y is non-zero, then x vector, which is P times y, cannot be zero because P is invertible, right? Then if Q is positive or definite, which means Q is positive for all x vector, then that is equivalent to saying that the expression on the right hand side of equation 4 will be positive for any non-zero y vector. Okay, so if Qx is positive for all non-zero x vector, then lambda 1 y1 squared plus lambda 2 y2 squared up to lambda n yn squared will be positive for all y vector. Now, if I consider y given by 1 0 0 0, then this expression lambda 1 y1 squared up to lambda n yn squared will be just lambda 1. So this positiveness implies that the first eigenvalue lambda 1 will be positive. If I consider 0 1 0 0 0 vector as y, then that will imply that lambda 2 is positive. So in a similar pattern, if this lambda 1 y1 squared plus lambda 2 y2 squared plus up to lambda n yn squared is positive for all non-zero y vector, then y1 up to y1 yn will be positive. So similarly, we can show that all these eigenvalues are positive. Okay. Now let us consider the converse. If lambda 1 up to lambda n are positive, then when we consider lambda 1 y1 squared up to lambda n yn squared, lambda 1 is positive, y1 squared is non-negative, okay? Lambda 2 is positive, y2 squared is non-negative, lambda n is positive, yn squared is positive, so it will be, or their sum will be non-negative, and this 0 is obtained only when y1 up to yn are all zeros. Otherwise, at least one of these y values will be non-zero, and then that term squared times the eigenvalue will be positive. So from this, the 1 y1 squared up to lambda n yn squared will be positive if we consider non-zero y vector, and that means for any non-zero x vector, qx will be positive if lambda 1 up to lambda n are positive. So the converse is also satisfied. So that means the first statement, if qx is positive definite, then the eigenvalues will be positive, and the converse is also satisfied. In a similar pattern, the qx will be negative definite if all the eigenvalues are negative, and the proof is similar. Okay. So the values of the quadratic form qx for non-zero x vector are determined by the eigenvalues lambda 1 up to lambda n. Okay, and the proof is completed.